Hello, my name is Matheus Oliveira and I'll be presenting the paper entitled Learning-Based End-to-End Video Compression Using Predictive Coding. So initially, I'll give a quick review on how traditional video codecs work. So given a video sequence, the frames are encoded by two major approaches. The first one is the interframe coding, where only spatial redundancy of the frame is exploited. So the frame is submitted to a transformation followed by a quantization, where the coefficients will be later submitted into an entropy codec. The second approach is the interframe coding. So giving a previously reconstructed frame available to both encoder and decoder, a motion estimation can be applied to the current frame in order to make a prediction for it. Thus, only the difference between the real frame and its prediction needs to be encoded. Usually, this residual is submitted to the same steps adopted in interframe coding. Our main reference for proposing our video codec was the work by Meaning et al. And all its previous versions. So the authors propose an image codec consisting of a variational autoencoder, which is jointly optimized for rate and distortion. The major improvements presented over the versions were focused on the latent probability model. In the cited work, for example, the parameters of the distributions were obtained by an auxiliary variational autoencoder. These works here have an enormous relevance in the image compression field. Now I'm going to present to you our proposed video codec. Our video codec splits the video sequence into groups of pictures. For each of these groups, the first frame is the interframe and all others are interframe, so they need the previous one as reference. Both encoding types, inter and inter, are implemented by two independent autoencoders. However, their architecture are inspired by the cited reference works. So we have an autoencoder here used for inter-prediction and an autoencoder here used for inter-prediction. Interframe coding is essentially performed by the reference architecture, since this approach handles the frame as an image. However, the architecture had to be adopted for interframe prediction. A target frame is concatenated in channel dimension with its predecessor and reference frame, and then the 6-channel tensor is submitted to the autoencoder, right here. So the output of the autoencoder, however, is the input to two other networks. So we have here the motion estimation network, which predicts the parameters for warping the reference frame, and the residual network, which aims to predict the residual between the warped reference frame and the target frame. Lastly, the output for both networks are added together and the reconstructed interframe is obtained. It's worth noting here that all blocks and transformation present in the proposed architecture are learned, which leads to an end-to-end approach. Some of the first results obtained by our proposed codec are shown here. Here at first we show some rate distortion curves which refer to the blowing bubbles video from the GVET dataset. We can see here that our rate distortion curve obtained by our proposed codec is in the same region as the ones obtained by the all intra modes of the newest and traditional video codecs HEVC and VVC. We also provide some visual comparison for an interframe of the basketball drill video. Although our codex uses far more bits for transmitting this information here, a visual comparison allows us to conclude that an end-to-end learned codec can indeed perform the task of video coding. So, thank you very much for your attention and have an excellent conference.